Hello everybody, and welcome to day 7 of climate change. Last time we were together, we talked about how energy that's absorbed by the Earth gets released in the form of infrared radiation, which can be absorbed by some compounds in the atmosphere, which we call the greenhouse effect. Today, we're going to look at the phenomenon that causes some energy that reaches the Earth to be reflected as visible light, while the rest of it gets absorbed and then gets released as infrared. So come on along, we're going to learn about albedo. Alrighty, so our quote for today comes from PayPal founder and Tesla CEO Elon Musk, who says, "We are running the most dangerous experiment in history right now, which is to see how much carbon dioxide the atmosphere can handle before there is an environmental catastrophe." So we're going to continue with our goal of being able to explain what is required for a stable energy budget on Earth. And we're going to do that by doing a lab, and then we're going to talk a little bit about albedo. So let's look at Earth's energy budget. Earth's atmosphere is important. Without our atmosphere, it'd be much colder here. Without our atmosphere, our average temperature on Earth would be negative 18 degrees Celsius. Instead, we have our atmosphere, we have an average temperature of 15 degrees Celsius, which I personally find much more pleasant to live in. And there's two things that really impact that. One is the amount of energy that gets radiated back down towards the surface from the greenhouse effect. And the other is how much energy that reaches the Earth in the first place turns into infrared. And that we call albedo. And so if we look at this example of Earth's energy budget, our energy is coming in from the sun, and some of that energy doesn't reach the Earth. Some of that incoming visible light hits clouds, bounces off, and reflects back into space. That energy cannot warm the Earth. Some of the energy makes it through the atmosphere, through the clouds, and comes all the way down to the surface. And when it gets to the surface, there are two things that can happen. One is it can reflect back off the surface in the form of visible light and go back into space. That energy isn't available to heat the Earth either. The only energy that we get from the sun that's able to heat the Earth is the energy that comes in and gets absorbed by the surface. So the energy that gets absorbed by the surface can be emitted in the form of infrared, which can be trapped by greenhouse gases. But depending on how much energy is absorbed, or the surface will really determine how much energy is available to remain in the atmosphere. And we call that property of the surface, how much of that energy gets absorbed, reflected, albedo. Okay, so we're going to come over here and we're going to do a little demonstration of albedo, which we're going to get started, and then we're going to go back and keep working on some stuff for a little bit, because like a lot of our demos here, this one does take some time. And I have at this table, I've got a couple styrofoam cups, and inside the styrofoam cups, I have just a piece of paper that I've rolled up and fit inside of it, and I've got a white one, and I've got a black one. So the only difference between these two setups is one of the inserts is white and one of the inserts is black. And I put a little bit of effort into even making sure that I had paper that was kind of the same weight. And so we're not dealing with a heavy construction paper for the black one and a light copy paper for the white one. I've used papers as similarly as I could find them. And as you noticed, they are inside of a styrofoam cup, and that styrofoam cup has been impaled from behind by a thermometer. This will allow us to measure the temperature inside of the cup by the black paper or by the white paper. And so right now, you can see that the temperature inside of the two cups is essentially the same. And channel one is the white paper, and channel 2 is the black paper, and channel 2's got the brown color, so that's similar to black, so we keep those straight. They're the same temperature, and what we're going to do is we're going to take a a sample. We're going to take, I think one sample every 10 seconds is good. But we don't need to run this for 20 minutes. We can run this for like 10 minutes is good. Okay? And what we're going to do is we're going to start this trial, and I'm going to turn on the light at the same time. So we're going to collect some data over the next 10 minutes, and we're going to see how the temperatures inside of these cups is impacted by the surface color. Okay. So while that's going on, let's progress a little bit. Here's kind of an extreme example. You can have a surface that is all nice, new, light, fluffy white snow, or you can have a surface that is dry, ground, dark, and these two things will absorb or reflect different amounts of light. And we can see that this snow-covered area is reflecting the majority of the light. And so because of that, only about 10 to 15% of the energy that's reaching the surface is able to be absorbed by the Earth and be radiated back as heat. Whereas if we look at a different surface, a darker surface, and it'll depend on if it's water or forest or grasslands, whatever, but if you look at a darker surface, you might see that 70% of the energy that gets absorbed by, or that reaches the surface of the Earth gets absorbed by it. This is why when you go outside with bright, new, fresh snow, even though it's the winter time and we're not getting as much energy reaching the Earth, it's very bright and hard to look at because a lot of the energy that's coming down and hitting the ground is getting reflected back into your eyes. And so, if we have more of the Earth covered with snow, then you would expect more energy that reaches the Earth to be reflected. So the less snow on Earth, or the less ice on Earth, the less energy is going to be reflected. So what is albedo? Albedo is a measure of the diffuse reflection of solar radiation off of the Earth. It's kind of a weird way of saying it, but what we're saying is light energy comes in, and it is a measure of all of these arrows. We can also say it's the ratio of radiosity, what's coming up, to the irradiance that's received by the surface. And if you kind of want a formula, it's the amount reflected over the amount reaching the surface, sometimes given as a percent. So we can state that fresh snow has an albedo, depending on the snow, because not all snow is the same, of somewhere around 80%, 70%. We can also see that water has an albedo of somewhere around 5%. And this is hugely important. This is also something that you know, right? You know if you look at water, it's dark. There is not much visible light coming back up and off of that water. When you look at water, you see this dark blue color, which means that all of that red light, all of the orange light, all of the yellow light, and so forth, it's reaching the surface, is being absorbed. The only light that you're seeing being reflected is blue, and if it's dark blue, not even that much of it. If I look at fresh snow, well, it's bright white. That means that all of the red light, all of the orange light, all of the yellow light, all of the green light, all the blue light, and all those colors are all being reflected back off into my eyes. Well, where does that energy go? Well, all the energy that got absorbed and didn't get reflected, all of those colors that I do not get to see, that's what gets to become the infrared radiation that heats the Earth. The other thing I want you to look at when you see this chart is that what the land is really plays a role in how much energy gets absorbed. So meadows reflect different amounts of energy than forests. Forests reflect less energy than savannas do. And so that's kind of one thing that is useful to keep in mind. And of course, clouds, which are very reflective. Okay, before we move on, let's come on over here and check out how we are doing. And, whoa, we haven't been going very long. We've been going about 300 seconds, but I'm already starting to see major differences between the cup with the black paper in it and the cup with the white paper in it. When we look in here, we can see that the cup with the black paper is significantly warmer than the cup with the white paper. And you have probably experienced this in your own life. If you go outside in the summertime and you walk with bare feet on blacktop, on asphalt, your feet get burned. It's very hot. But you don't have that same effect if you walk on, say, a similar feeling surface like concrete that happens to be white. And so we know that one can absorb more energy than the other. But the thing that we're focusing on is the kind of the opposite of that right now. We're not thinking about what's being absorbed, we're thinking about what is being reflected. So more of the energy that's entering this cup with the white paper in it is leaving as visible light compared to the cup with the black paper, where more of the energy that's entering is staying inside of that cup. All right. I don't think we actually even need to run this the full 10 minutes. We look at this and we're seeing that we're already reaching a steady state. We're seeing that the cup with the black paper is kind of leveling off at about 4 degrees warmer than the cup with the white paper. And we're right there. We don't expect either one of them to increase very much. Maybe we'll get another degree out of the one with the white paper, but not very much more. So with that, let's stop the trial. And we're going to go ahead, we're going to get back and finish taking a look at the rest of our work for today. Okay, so what is the impact of this? Well, one of the biggest places where we see an impact from albedo is at the poles, because we have an interface between ice and snow and water. And you saw on the last slide that ice is very reflective, has a very high albedo, and water is very not reflective and has a very low albedo. And so when we change the amount of ice, we are able to dramatically change the amount of energy that gets reflected, and therefore the amount of energy that gets absorbed. So let's talk about ice for a little bit. Ice is important in keeping the Earth cool in 2 ways. It keeps Earth cool by the latent heat of fusion, so that buffers the temperature. So you know that when you melt ice, that you have to put a lot of energy in to make that melting occur, which is why ice does such a good job of keeping your drink cold, right? So the actual melting, it takes energy to pull those particles apart. And the other one's albedo. And so when a smaller area of the sea is covered by ice, or of land, more energy gets absorbed, and the Earth warms up, which causes more ice to melt. We call this a positive feedback loop. Temperatures rise, ice melts. As reflective ice disappears, there's more surface of darker ocean to absorb heat. Therefore, more heat gets absorbed, which causes temperatures to rise. Temperatures rise, causes more ice to melt, and we have a cycle. So whenever we have a self-reinforcing system, we can call that a positive feedback loop. One thing happens, it just keeps going more and more and more and more and more. So, knowing what you know about the latent heat of fusion and albedo, and how energy gets transferred from the equator to the poles, I want you to be ready to discuss with us in class what will happen on Earth if all of the ice were to melt. Keeping in mind that we have sea ice and land ice in Antarctica, and we have a lot of sea ice in the Arctic and land ice on Greenland. We're keeping it a little bit short today because I am going to, for your homework, ask you to do a little bit of reading too. And so I want you to go ahead and read pages 10 through 12 and 37 to 58 from Demystifying Climate Models. We're going to begin a discussion about climate modeling, and in order to do that, we need to have a little bit of a baseline. So go ahead and read it. It's not too terribly long, but I do want you to be ready to discuss it when we come to class. All right, everybody, have a wonderful day, and I look forward to seeing you together. Bye-bye.